Okay, everybody, we left off at this point when we were speaking yesterday about the patterns and how to come up with either recursive or explicit rules, except for period 5. You guys got to this point, so this might be a little repeat at the beginning for you guys. Okay, and what we talked about in period 5 is that we were able to come up with an explicit rule for this pattern, and they did it in kind of an interesting way. One way you can do this is you can guess and check. You can look at the inputs versus the outputs, or in other words, the index or the term number, n, and the actual term, or the a sub n, like we were talking about in class. And if you look at this, you're given up here 6 different terms in the pattern. And you can see the amount of blocks used to build each of those. So the first one is 1, and then 3, then 6, 10, 15, 21, etc. So things that you can do are things where you take the input and try to think of operations you can perform with that number and produce the output. And what you might find works for one then might not work for another, and then you haven't found the explicit rule. But you can keep trying that. And things to try are multiplication, addition, subtraction, and even squaring things sometimes if you think that that's going to get you closer to what you're looking at. Mathematicians have an interesting way at looking at this problem in particular in a way that they kind of, we talked about how they proved it or showed that it worked for all problems. And so one thing they would say is, well, you can find any term number you want by starting with 1, because notice that the first pyramid had 1 block. The second pyramid had that same 1 block plus a row of 2 blocks. The third pyramid had the same 1 block, the same 2 blocks, and then a row of 3 blocks. And this would continue on until you reached your final pyramid, which would end with a row of n blocks on the bottom if we're looking at an. Now, I'm going to write a couple of things that come before n. So if I know that n is down here at the end, then I know that the term right before that is n minus 1, and the term right before that is n minus 2. Okay? So mathematicians said this is a way you can do it. So if you're trying to find like the 100th term in this sequence, you're going to plug in 100 for n, or in other words, add the numbers from 1 to 100. But then they looked at a really interesting and quick way to add groups of numbers like this together. They said, well, what if we wrote it the other direction? And started with the n on this side, and then the n minus 1, and then the n minus 2, and continued down to 3, down to 2, down to 1. Both of those are representations of the same thing. Then what they noticed is that at each term, if you add the terms together, okay, you get the same thing. 1 plus n is n plus 1. 2 plus n minus 1, once you combine like terms, is also n plus 1. 3 plus n minus 2, once you combine like terms, is also n plus 1. This continues, and you can see down here at the end, n minus 2 plus 3, which is the same combination we previously had, is n plus 1. N minus 1 plus 2, again, is n plus 1. And at the end, n plus 1 is n plus 1. But this is no longer equal to a sub n. It's actually equal to 2a sub n's, because we used 2 of those expressions added together to get this result. So we generally don't like to write out all of this repeated addition. Instead, what we like to write is, well, I'm using the number n plus 1, and how many times am I using it? So you can't really see here with the dot, dot, dot going on how many times we're using it, but you can see from the expressions we got it from that they were numbered from 1 to n. Therefore, there are n terms here. Okay? So you can do the simple operation of n times n plus 1 in order to find out double the number of blocks used in the nth term pyramid. And so we said the last step here would be to divide by 2 to see that you can plug 100 into this formula to figure out how many blocks it would take to build that 100th figure in this pattern. But this isn't the only way to look at this. So if we look at this next one, okay, example 3, it asks for an explicit formula for the given sequence, which is 0, 3, 8, 15, 24, etc. So in other words, there are a couple ways for us to think about this. Okay? One way, again, would be to look at kind of input-outputs, which we're not going to call x and y anywhere. We're calling n and a sub n. So we want first term, second term, third term, fourth term, fifth term. And in this case, that's 0, 3, 8, 15, 24. And again, you can try and think of things that you can do, mathematical operations to the n values to obtain the a sub n values. Okay? Something that stands out to me, but I've had a lot of work with patterns, and it might stand out to a lot of you too, is that when I started looking at this, I was thinking, I don't see any immediate, multiply by this or add this, but I thought about, what if I squared 5? That would give me 25. Not quite 24, but really close. What if I squared 4? That would give me 16, which isn't 15, but is pretty close. So then I thought about the fact that all these numbers that I'm seeing over here as the terms in our sequence are one less than a perfect square. And comparing them to which term number they are, it seems if I do n squared minus 1, that would work. Okay? Another way to do this might be to look at each term in its most factored form. So we have 0, which could be 0 times anything. 3, which is just like 1 times 3. 8, which would be 2 times 2 times 2. 15, which would be 3 times 5. And 24, which would be 2 times 2 times 2 times 3. Now, I don't really see any big pattern happening there. So the idea would be that I would want to write these in a simpler way where I could try and see a pattern occurring. Okay? Keeping in mind that this is the first term, this is the second term, this is the third term, the fourth term, the fifth term. Okay? When I do look at this, I see that there are a couple terms that do look similar. 3 times 5 is similar to 1 times 3, not just because they both have a 3 in them, but more so because they both have 2 factors. And notice how they're related to the term number they are. This is the second term, and it's using 1 and 3, the number before 2 and the number after 2 multiplied together. And here at the fourth term, it's using 3 times 5, or the number before 4 and the number after 4, to be multiplied together. So I'm going to see if I can try and make everything fit that pattern, and if that's actually something I can use. So in the first one, that would mean that this would have to be able to look like 0 times 2, because 0 is the number before 1 and 2 is the number after 1. That would work. The second term, we already determined that 1 times 3 fits that pattern. In the third term, if I'm looking at the 3, I would want to use 2 times 4 if this pattern really works. And notice that that does have the same value as 2 times 2 times 2, or as 8. We already determined that 3 times 5 fits our pattern for the fourth term. And if this is the fifth term, the number before 5 is 4, and the number after 5 is 6, and 4 times 6 is equivalent to what is in that term. So what I see here is that every term can be built this way. And think again about what we said, and we'll use this second term as an example. This is the second term. In other words, n is 2. But the numbers that I multiply together to obtain this are 1 less than 2 and 1 more than 2. So the way that I would write that out mathematically is that it's n minus 1 to get the number 1 less than 2, and n plus 1 to get the number that's 1 more than 2. So this would be another representation of the rule. And if you multiply that out, you'll see that that's the same as n squared minus 1. So as you guys are going through the homework, try to either use guess and check methods or different types of patterns that you see now that you've seen a few ways of looking at the problem to determine how to come up with those explicit rules. And then you can use your notes for the recursive rules. And you guys are working on homework number 1. It's listed on the chapter 2 assignment sheet, but it's actually from section 9.1. And then I will be back tomorrow to answer any questions and to move us forward into section 9.2.